All right, everyone, today we're going to talk about analysis of variance. And you should know that in order to use an analysis of variance, you need 3 or more groups. So, we know we have one sample, use a one sample test. We have 2 samples, we have a 2 samples test. We use anything greater than 2 samples, like a 3-group experiment, we have to use ANOVA. And y'all, just for the future, we should just use the terms between, within, total, subjects, and error. I was simply describing what they were a little bit in detail so you would get an idea. Between is the between groups variation. Within is the within groups variation. Total is the total variation. Subjects is the participants variation. Error is crap that's left over. I don't mind if you use different words, really. Like if crap is better than error for you, I really don't care. But ultimately, these are the words I'm just going to use, and I'm going to be able to use them by just shortcutting, by using the shortcut. So the foundational aspect of ANOVA is sum squares. Sum squares is just the foundation of all the logic of the ANOVA. And you got to understand, analysis of variance just simply means analysis of variance, and variance is just sum squares divided by degrees of freedom. So essentially, the foundation of this entire test is sum of squares. Today's example is one I chose for my neuroscientists who work with rats. It's a within subjects design. Mice get dosed with cannabis. With no cannabis, that's the control, with 10 grams of cannabis and 100 grams of cannabis. And we measure their sleeping during a 24-hour period. That's the design we'll be using today. Now you can see here our data. Our data are fairly simple. We have Mighty Mickey, Minnie, and Modest Mouse. We have every one of them participated in all the other conditions, just at random times and with good breaks and all the rules of good science. Don't worry about those. But essentially, here's our data after we ran the best within subjects drug dose design that we could. Here's our numbers. These are the hours of sleeping that each mouse slept. I'll say this a few times. Variance is just sum squares divided by degrees of freedom. So we're going to focus on the sum squares first in this lecture. Our first measure of sum squares is called the total sum of squares. It's the total variation in the entire data set. So it's not the variation due to our treatment. It's not the variation due to any error. So it's not signal, it's not noise, it's everything. Signal and noise plus everything else. So it's just total sum of squares, just simply saying in our data set how much variation exists in the entire data set. What is the total sum of squares? We have this design, we have this data. And when we're calculating the total sums of squares, we have to ignore all our conditions, and we have to ignore all our different subjects and just view this as one specific data set. So this is just one data set. Let me show you on the next slide. So here you can see that it's the same data, but I just ignored everything about it. So I'm looking for my total sums of squares. So I'm saying within this data, what is the sum of the squared deviation scores from the mean for this entire data set, ignoring everything about my conditions, everything about my participants. So I just ignore that and I say, okay, I got these scores. I calculated my average, which was 11.25. I calculated my deviation scores. You can see that in the second column. 8 minus 11.25 is negative 3.25. I continue doing that for every single score. I sum those scores to make sure they sum to 0, because they should sum to 0, because the average deviation from the mean is always 0 because it sums to 0. And we have our squared deviation scores, which are just the squares of our deviation scores. I add all those squared deviation scores together to get a sum of squares. Easy peasy lemon squeezy, okay? That's it. That's the total variation that's present in all of our data. We don't know why it's present. We're trying to parse that out. We're trying to figure out, what percentage of this variation is due to our treatment effects. When I say treatment, I'm talking about our independent variable, our experimental conditions, right? And I also want to know how much of this sum of squares is due to error, things that I can't even predict? What's my signal? What's my noise? I'm asking these same questions, but it starts with the total sums of squares. Total sums of squares is just the total variation present in our entire data set. So here we go again. Our total sums of squares is 430.25 squared units of variation in our total data set, squared units of sleep in our total data set. It's how much variation exists in the entire data set. Let's switch gears to our second sum of squares term. It's called the between groups sum of squares. It's variation in our data set due to our independent variable. It's variation in our data due to our manipulation. It's variation in our data due to any categorical or predictor variables that we have. So in this example, it's going to be the variation due to the different drug doses. There are other examples from your research, but they're all independent variables. Right? Your between group sum of squares is saying what percentage of the total variation in the data is caused by your treatment conditions. All right, so we start with our original data here. And what I did was I went from my original data to a summary of my treatment effect, or a summary of my effect of my manipulations. The only way for me to do this is to average across all the individual mices, whatever the appropriate term is. Mice, I know it's the right term, I'm just having fun. All right, so I averaged across all three of those conditions. So my control condition average is 6.5. My 10-gram cannabis condition is 9.75. My 100-gram cannabis condition is 17.5. And then I'm just taking a pause. I'm going to slow it down. What does this data mean? Well, these three means represent the effect of my independent variable. They represent the effect of my treatment. They represent the effect of my conditions on sleeping. They represent the effect of drug dose on sleeping, 0, 10, 100. So what I'm going to do now to figure out the sum of squares that's due to my treatment is I'm going to treat those means as if they were their own small little data set. So you can see I do this in the last step on this slide, right? I'm saying, okay, my control mean is 6.5, my 10-gram cannabis mean is 9.75, my 100-gram cannabis mean is 17.5. And what I want to do is find the sum of the squared deviations of these means from the mean of these means, right? And that's going to be the sum squares that's due to my independent variable, that's due to my treatment, that's due to my manipulation, right? Everybody's with me, I hope, because we're moving on to the next slide. This should now be old hat. I have my condition names, I have those means. I want to calculate the sum of squared deviations of those means from their mean. If you look, when I average those three numbers together, we see a mean we've seen before, 11.25. That's our grand mean. So now I'm saying, well, what is the variation, the deviation of each of these scores from the grand mean? 6.5 minus 11.25, 9.75 minus 11.25, 17.5 minus 11.25. Boom, I'm going to check them. I add them up. Do they add to 0? Yes, they do. You can see that. And then I square them and add them up, and I get a sum of squares of 63.875. And we're almost done. We're almost done. Now, but hold your horses. When you look at this data and you need to understand the actual between group sum of squares, you have to see one very important fact, that we have a set of scores of Mickey that are impacted by these three means. We have a set of score of Mighty who is impacted by these three means. We have a set of scores from Minnie that are impacted by these three means. We have a set of scores in Modest Mouse that are impacted by these three means. These three means that we calculated the sum of squares for actually have 4 times the impact than what we thought earlier. So because we have these 4 different participants who each have 3 different scores that represent the different means for the different conditions, we do not have a sum of squares of 63.875. We have a sum of squares of 63.875 times 4. So our between group sums of squares is 255.5. 6.50. We have another sums of squares that we can calculate. It's called the within group sums of squares. And I'm going to call it error within each experimental condition. And this is going to be in line with how I have talked about error throughout this class. Let me show you that one real quick. So we have 3 different treatment conditions that have 3 different mini data sets, and I've blown them all apart here. You can see I'm viewing this as 3 separate data sets. Each of these little data sets have a mean. Each of them do, and we just talked about those 3 means. Now my question is, within one little data set, like within the controlled data set, we have variation from the mean that we don't know why. We didn't control it. In a perfect world, we'd have no variation here, but we have variation, and we call this the within groups sum of squares, or we're looking for the within groups variation, right? So if I look at this control group, we know numbers differ from the mean, but we don't know why. So this is our estimate of error. So we can get one estimate of error from the control group, one estimate of error from the 10-gram condition, and one estimate of error from the 100-gram condition, okay? So that's all I'm saying. Like, why do these numbers differ from their group means? We have no idea, but let's quantify that error measure, right? Let's quantify how much error is in each of these conditions. Let me show you how to do that. Well, you shouldn't be too surprised how to do that because it's just a sum of squares. We calculate the sum of squared deviations from the mean of everyone in the control condition. So the average in the control condition is 6.5. The deviation score 8 minus 6.5, 10 minus 6.5, 5 minus 6.5, 3 minus 6.5. I make sure that these deviation scores sum or average to 0. And if they do, I go on, I got it right. So now I'm squaring each of these deviation scores, and my sum of the squared deviation scores, which are due to error in just our control group, is 29. So there's 29 sums of squares of error present in the control group. I do the exact same thing for my 10-gram condition. I find the average of these numbers, which is 9.75, and then I find the deviation of each score from 9.75, so 11 minus 9.75, 16 minus 9.75, 6 minus 9.75, 6 minus 9.75 to get my deviation scores. I average them or sum them together to make sure they average and sum to 0. If they do, I then square my deviation scores, sum them together, and we can see that within the 10-gram condition, there's 68.75 units sum squares, and that's sum squares due to error. So there's 68.75 sum squares in the 10-gram condition that's due to error. Now let's do it one final time for a 100-gram condition. We find the average of 17.5. We calculate the deviation scores. We make sure they average and sum to 0. Then we square the deviation scores and add those together, and we get 77. So let's kind of keep track of where we were. Each of these individual groups had a mean. And each of these scores in these groups had variation from that mean that we did not control. It was not part of our manipulation. We don't know necessarily where it's coming from. We have no idea. It's just error. So what was our total error in the experiment? It's the sum squares within the control group, the error in the control group, plus the sum squares of the error in the 10-gram group, plus the sum of the squares of the error in the 100-gram group, leaving us with 174.75 sum squares within is what we call it. We call it the within group sums of squares, but I want you to know it's an estimate of error. So if this was a between subjects design, this is where we would stop. These would be all the sum squares we would need, right? We would have total equals between plus within. And I want to point out that I like to check my calculations. So here you got 255.5 plus 174.75. If you throw that in a calculator, you find out that I am correct, that this formula works, that these estimates are great. We're going to use these estimates to figure out some statistics, but right now we're just trying to figure out, hey, what are the sources of variation in our data? Well, we have the total variation in our data, we have the variation due to our independent variable, and we have the variation not due to our independent variable. Individual differences, crap we're not controlling. So we see our original formula, sum squares total equals sum squares between plus sum squares within. But now we have a subformula for subsquares within. Subsquares within equals subsquares subjects plus subsquares crap or plus sum squares residual plus sum squares all other error plus sum squares we don't know plus sum squares error is what we most commonly call it. So in this case, what I know is that I had 174.75 within group sums of squares, variation within each group that we didn't know how to account for. Then we found out that we had 124.92 sum squares or variation due to our different participants' average sleeping habits in the study. Well, I know where that 124.92 sum of squares variation is coming from. It's coming from my different mice, and I was able to quantify it. That means as a scientist, it's no longer error. I know exactly where it's coming from, right? So guess what? I now have a smaller but better estimate of the sum squares error by taking sum squares within minus sum squares subjects equals 49.83. So the whole purpose when you have a within subjects design is to remove individual differences. This is the estimate of individual differences in sleeping, and we were able to remove this error from our data. And so we were able to account for it. This is no longer error, this is just variation due to having different participants in the study, and we can directly estimate that, and it's beautiful. So how am I going to do this? It's going to be very similar to how I calculated sum squares between. So if you look here, I have Mighty. I want to know Mighty's average sleeping, so I average Mighty's 3 scores together to get Mighty's average sleeping time. I do the same thing for Mickey, Minnie, and Modest. And then I treat those means as if they were their own data set. And so I'm going to calculate the sum of squares of those means from the mean of those means. Let's see what that looks like. So here we got those means of Mighty, the mean of Mickey, the mean of Minnie, the mean of Modest, right? Boom, we got them there. The average of these averages is 11.25, so that's our grand mean. So now we're going to take the participant's mean, Mighty's mean of sleeping minus the grand mean, Mickey's mean of sleeping 15 minus the grand mean of 11.25, Minnie's mean of sleeping 10.67 minus the grand mean 11.25, Modest's mean of sleeping 6.33 minus the grand mean of 11.25. We're going to get our deviation scores. We're going to make sure they sum and average to 0, and we do have that case. We square them, and we sum those squares together to get a 41.64 sum of squares due to individual differences. But hold your horses. Just like we were talking about in the between group condition, right? We have one set of 41.64 impacting the scores in the control condition. We have one set of 41.64 impacting the 10-gram condition, and we have one set of 41.64 impacting the 100-gram condition. So our sum squares subjects actually equals 41.64 plus 41.64 plus 41.64, and that equals 124.92. This is the same move I made when calculating the between subject sum of squares. Okay, so we've talked about all the sum squares, and you probably get where they come from, but you don't see why it matters because I didn't start with why it matters. I just wanted to start with the sum squares, right? What you need to understand is that we have variation due, the total variation due to our independent variable, and variation due to subjects, and variation that we don't know where it's coming from. We're going to use these to do a more complicated calculation. So let's just talk about what each sum squares means. Sum squares total equals the variation in all our data. Numbers vary due to our experiment, due to individual differences, and due to crap that we didn't control or measure. So it's just all the variation present in our data. The variation from the grand mean of the data. So our sum squares between is the variation due to our independent variable or our experimental manipulations. Sum square within is error in a between subject design. It's all the error we don't know, all the variation in the data that we don't know where it's coming from, right? We have sum squares of our subjects, and that's the variation in our data that's due to our different participants' individual differences in the dependent variable. So we're able to estimate this and remove this to get a better estimate of error, and we remove this to get a better estimate of error, and that new estimate of error is called sum squares. We don't know why these numbers are varying. We can't quantify that. We know that there's a total variation. We know that our independent variable causes some variation, sum squares between. We know that there's error within each group, but we don't know where it's coming from. We know there's error due to our participants' individual differences that we can quantify and remove. And then we have sum squares error, which is just the crap that's left over that we don't know where that variation is coming from. It's our estimate of noise. So if we're looking at this as signal to noise, we got SS total, neither signal nor noise. SS between, signal. SS within, noise in a between subjects design. SS error, well, no, SS subjects. Well, that's not error. That's not our manipulation either. That's neither, but it's just the variation due to individual differences. Then we have SS error, which is our at best estimate of noise after we've removed individual differences from a within subjects design. Also, just so you know, imagine you had one of those funky counterbalance designs with multiple orders in there. You could do the same thing with order. You could find, oh, how does order impact sleep time? So did they sleep more in the first dosing condition, independent if it was control 10 or 100, right? Did they sleep more in the second, sleep more in the third? If there is a general trend towards more sleeping, we can remove the order effects from our data, from our error term, in this very same way that we were able to remove subject effects from our error term. So I'm just letting you know that this is a creative and useful thing to think about. Now, this last one, I'm not going to show you how to remove sum squares order. It's an advanced move, but I want you to know that you can, okay? Everything I've talked about up to this point has assumed equal n. And I want to point out that things get particularly complicated when you do not have equal n. Now, first, if you have unequal n, then you cannot have a within subjects one-way ANOVA. You just can't. You just won't have the same. If you had the same people in all three conditions, then you would have to have equal n by definition. So just get that out of your mind. So this is only applying to between subjects designs with unequal n. And second, the real big issue is you can't just multiply your between group sums of squares by the number of participants in each condition because you don't have the same number of participants in each condition. So essentially, I'd never ask you to do this by hand, but if you wanted to, you would take your mean for your control group, put that in place for your 3 observations. I took one away here, right, just to simulate an unequal n design. So this is a whole new data set, but we're going to assume the same numbers. Here, I'm going to assume I have 4 participants in the 10 grams condition, 9.75 4 times. And here, I'm going to assume I have 2 mice in the 100 gram condition, 17.5 and 17.5 2 times. In order to find my sum squares, I have to find the average of all these means, and I have to then do the deviation of these means from the average of all these means, the grand mean still. Then I have to square those and add those up. So I actually have to do that individually now like I would in a total sum squares. So essentially, I would treat this data like a total sum squares calculation. There's no quick way around it when there's unequal n. Now, don't let that worry you. I'm not going to give you unequal n problems by hand, but some of you like to know what's going on when you're doing it by hand. But essentially, right now, we've talked about all of our sources of sum squares in an ANOVA, and we're moving on to the next idea. The next idea is degrees of freedom. And remember, sum squares divided by degrees of freedom is variance, and this is the analysis of variance. So guess what we're going to be doing? Calculating the degrees of freedom for every single sum squares we just calculated. So variance equals sum squares divided by degrees of freedom. You saw this earlier in the standard deviation formula. It's the same idea. We're finding variation from that mean. It's the average variation from that mean. Just sometimes it actually means, it doesn't necessarily mean error now. It actually can mean, oh, treatment effect, or it can mean subjects effects. So we're doing the same math that we did very early on in this course. Let's talk about the total variance. We get that's the total variation in our dV. That is simply our sum squares total divided by degrees of freedom of this data, which is all of the data. So this is a question, what is degrees of freedom? So here's what we got to understand. Yes, we do have actual data here. And these data have an actual mean that we calculated earlier, 11.25. So yes, we have actual data here, but when you are figuring out degrees of freedom, you have to say, riddle me this. I imagine I have the same number of observations that I collected, but now the numbers are free to be any number in the world. How many of them are actually free and how many of them are fixed such that the mean of all these 12 numbers right here is still 11.25? Riddle me that, right? Well, I didn't actually take the numbers out or change them, but technically, 11 of these 12 numbers are free to be anything just due to the rules of math, right? This 10 at the bottom could be 1,000,000. This 6 could be negative 1,000,000. This 3 could be 1,000,000,000, so forth and so on until we get to that last number, which then it's fixed to have a specific value that will make the entire data set average out to our grand mean of 11.25 that we calculated earlier. So in this case, for the total variance, the degrees of freedom for the total component is 12 minus 1, or the total number of observations minus 1. So our total variance is 39.11. That's important to know, but it's also important to know that this is not going to be used after this point. I just want to show you we can calculate variances for everything. We're going to use some of them. We're going to use the signal and noise ones. We're not going to use the other ones. So I'm still going to show you how to calculate them because I want you to have the degrees of freedom lesson. Now, this is one that for sure matters, right? Our between groups term. So our between groups variance is the sum squares between groups divided by the degrees of freedom of this data that we use to calculate the sum squares between groups, this data that's on our board here. Now, I have some things written out, but ignore that stuff for right now. What I want you to see is that I have some red numbers and some green numbers. The red ones are not free to vary. They do not have freedom. The green ones do have freedom, and I want to talk about this some more. So first, right, number one, remember when I calculated the sum squares? You know, and I said Mighty had one of the sum squares, Mickey had another, Minnie had another, Modest had another, right? But one of the things you got to realize is that the numbers that we're using to do that sum squares calculation are all right here on the screen. And what we know is that first score for Modest, Minnie, Mickey, and Mighty, they all have to be 6.5, right? The same thing for the 10-gram condition. All those numbers have to be the same. And the same for the 100-gram cannabis condition. All those numbers have to be the same. So for the sake of illustration, I just said, well, okay, I'm just going to choose mighty just to be the one that can possibly have numbers that vary and say, look, because, you know, the number I put in for mighty was 6.5. All the numbers that came for everybody else had to also be 6.5. The same thing for 9.75. They all had to be 9.75. The same thing for 17.5. They all had to be 17.5 just because how we did the calculation earlier. So none of those 9 numbers at the end are free to vary. So now I'm focusing in on mighty's scores. And I'm saying, okay, of these 3 numbers, how many of them were free to vary? And still have all these numbers add up to the grand mean like we showed earlier. Well, only 2, right? And this may seem a little counterintuitive, but you know, that control group for mighty could have been anything, but it was 6.5, right? That means the other 3 after it had to be 6.5. The second one could have been anything. It was 9.75. Hypothetically, it could have been anything, but that means all these other 3 numbers were stuck to 9.75. Furthermore, our last one, well, it's fixed. These numbers have to average to 11.25, like we saw earlier. So this 100-gram cannabis one is fixed. It's not free to vary. Only 2 of these 12 numbers that we use in the sum squares between calculation are free to vary. So it's literally the between groups degrees of freedom is k minus 1, even though we're using 12 different numbers to calculate this sum squares. But if you look, only 2 of them are actually free to vary. So that's pretty cool. So the degree, if you want a formula for degrees of freedom between, it's just number of groups minus 1, k minus 1. So now we're on to the within groups variance, and particularly the degrees of freedom within groups, right? So variance is sum squares divided by degrees of freedom. The question we're asking is, hypothetically, how many of these numbers are free to vary? And so we go back to our sum squares within calculation. And remember, we calculated the variance within the control group, the sum squares within the control group, the sum squares in the 10-gram condition, the sum squares in the 100-gram condition. We did those individually, then we added them up. Well, here, we're still asking our riddle. Imagine that first set of data, that error in the control group data, imagine that had to average, the data in there, had to average to the sample mean that we found earlier. But, you know, right now we're going to wipe the slate clean and assume we have no more observations, no set observations in there. How many of these observations in this new sort of condition are free to be anything? And how many are fixed if we want the mean of this new hypothetical data set to equal the mean of our known data set? That's the riddle. So in this case, it's 3, right? That bottom number could be 10 billion. The second one could be 10 billion. The third one could be 10 billion. And then that fourth number is fixed to be a specific number that averages with the other numbers to be the same average we found earlier, right? That's how means work. So that's one of those observation is fixed in the error in the control group, and 3 are free to be anything. Same riddle, same question. New set of data, new mean because it had a different mean, but still the idea is the same. Imagine if these numbers could be any number in the world, how many of them are free to be any number and how many of them are fixed if we want the mean to stay the same of this second data set? Well, it's the same answer, n minus 1. 3 of them are free to be anything and 1 is fixed, and it's just for that same reason. Oh, 56, negative 57, 4. That sets my last number is, for it to have the same sample mean, it has to be a specific number. It can't, it has no choice. So again, we have 3 of these are free, 1 is fixed. And you know, I'm not going to do it again for the last problem here. Not the last problem, but the last component to our within groups variance. But you can see it right here that it's the same answer. It's 3. 3 of those 4 are free to vary. 3 of those 4 are free to vary. 3 of those 4 are free to vary. So we have n minus, we we can see that we have 9 degrees of freedom. There's also a formula for this: total number of observations minus the total number of groups. So that equals 9. And then our sum squares, well, excuse me, our variance equals our sum squares of this component divided by 9, our degrees of freedom for this component. So now we've moved on to our variance due to our subjects, individual differences in the dependent variable that we can measure. So we've measured our dependent variable. We have the same people in all the different conditions. We now know who sleeps more than others. And in that case, if we look at the data, we can see that Mighty sleeps more than Mickey. Well, actually, Mickey sleeps more than Mighty, who sleeps more than Minnie, who sleeps more than Modest. So all we're doing is trying to figure out the variation in the data, the variance, that's due to individual differences in sleeping behavior. We already have the sum squares for this term. Now we have to figure out the degrees of freedom. If you look to the right, this is the data set, the complete data set that we used to calculate the sum squares for this subjects or participants component. The question is, how many of these scores in this data set are free to vary? And one of the things you're going to notice is that all of Mighty's scores are the same, all of Mickey's scores are the same, all of Minnie's scores are the same, and all of Modest's scores are the same. And that's because by design they have to be the same. So I just picked the last 2 columns and said none of those are free to vary. Those are the ones that weren't free. And I just said the ones in the control condition were the ones that were possibly free to vary. They're not free because they couldn't be anything other than the same number as was present in the control group. So those last 8 numbers are not free to vary. Within the control group, we're like, okay, how many of these numbers are free to vary? That's a good question. And the idea is the same. If this whole conglomeration of data has to have the same average that it had in our calculation of sum squares, how many of these numbers are free to vary? We've already talked about why the last 8 are not free to vary. Within the control group, 3 of them are free to be anything. Yes, you're noticing one's 13, one's 15, one's 10.6. But let's imagine the first one was 11. That means all the other ones after it would have to be 11. The second one for Mickey was 12. Everything after that 15 for Mickey has to be 12. Minnie, let's say that was 19. All Minnie scores would have to be 19. Let's say Modest's was actually 2. All Modest scores would actually have to be 2 if that were the case, except Modest's scores aren't free to vary, right? Of those 4 scores, the first 3 were free to be anything. But the last one was fixed so that the mean of all these numbers was the same as it was before, the grand mean. So here we have an interesting case that was similar to our between groups variation that we saw before, but now we have 3 of these 12 numbers that we use to calculate the sum squares subjects are free to vary. And that is the number of participants. There are 4 different participants minus 1. So then to calculate the variance of the subjects, we just take their sum squares divided by their degrees of freedom. We don't really use this measure variance. This is something that we're doing to make our error term cleaner and better. So essentially, we don't care about the subject's effects. We don't care that some mice sleep longer than others. That's not something we care about in terms of our research question, but we care about it in terms of being controlled, in terms of having a tight experiment. We know that this variation is due to individual differences in sleeping, and we can remove it from our estimate of the error term. So let's go to our next slide where this will make more sense. So now, with a within subjects design, we have a better estimate of error. Error is just variance in our DV that we have no idea where it's coming from. So we take, in a between subjects design, that's just our within subjects estimation, right? But now we remove the variation due to our participants because we know where it's coming from and we don't care about it to get a new estimate of error. That's all that's going on here. So in order to find our sum squares for error, we have to take our sum squares within minus our sum squares subjects, and that equals about 50. Then we have to take the degrees of freedom within, which is 9, minus degrees of freedom subjects, which is 3, to get our degrees of freedom error, which is 6. And our variance error equals those two numbers divided by each other. This is our best estimate of noise. All this has been leading us to figure out something called the F statistic. And the F statistic is not that complicated. Hint, it's a signal to noise ratio of variances. So wait, the signal variance is going to be variance between, and the noise variance is going to be variance error in a within subjects design, or variance within in a between subjects design. Sweet. So why does all this matter that we were talking about? I didn't really give you context because today I felt like building to the end resolution. So first things first, we have a new statistic called the F statistic, or F ratio, and it is simply the variance between divided by the variance error. Now, what does that mean conceptually? Well, variance between we got by examining the variation between our condition means, so that the condition means are our estimate of signal. Variance error in a between subjects design was just the variance within each of those conditions with those means. So why did the numbers differ from those group means? We don't know. That's error. In a within subjects design, it's not just the within group's variation, not that within variation component. It's that within variation component minus the individual differences in sleeping due to our different subjects that we can measure. So essentially, in our within subjects design, our measure of noise is better than our measure of noise in a between subjects design, okay? But don't let that fool you, and don't get between and within confused across the interpretation of experimental design and across the interpretation of a sum squares component. Between is when you have different participants in different conditions. That's a between experimental design. And within groups, matched triplets, I guess, correlated samples design is still that same idea where you have the same or related people or related observations in each of your 3 different groups, okay? So essentially, this is a signal to noise ratio, but we have to make it a little bit more complicated for the F statistic to make sense. And I've been waiting all semester to share this with you. It's not just the signal to noise ratio. We have to realize that our estimate of signal is also affected by our estimate of noise. So the real ratio that we have, it's not signal to noise ratio, it's signal plus noise over noise. And I'm going to call it signal plus error over error in this discussion because I want you to see that error is noise. So I think by changing up my words slightly, you'll see the connection between what we know about signal and noise in our previous studies and what we know about signal noise now. Now, this simple ratio is called the F statistic, the F ratio, the F test. And it is the variance between divided by our variance error. And I know I said that before. And I also said that the error variance in a between subjects design is simply that within groups estimate, that within groups factor. Now, in a within subjects design, the error variance is that crap factor, or that error which we get from taking the within factor minus the subjects factor. Nonetheless, it's still a signal to noise ratio. SPSS does call these mean squared, so the mean squared between divided by the mean squared error. There's different names for different statistics. I wish we didn't have synonyms, but we do. Nonetheless, the idea is still the same, and I want to walk you through. Let's put some numbers in here to make this all make sense. So an example. So F equals signal plus error over error. If we assume that all error is the same, let's just give it a number. Let's say the error in the numerator is 5 and the error in the denominator is also 5. So let's also assume that we have no signal at all, no treatment effect. Our independent variable did not impact the data at all in any way. So in this hypothetical example, we have a 0 plus a 5 divided by a 5. So at 5 over 5 equals 1. When F equals 1, there is no treatment effect, right? And the signal to noise ratio would be 0 to 1 essentially. So there's no estimate of signal here. So when there is no estimate of signal, our F ratio is always 1. So an F of 1 is when we talk about the null hypothesis, that's going to be the part where the null hypothesis is true and there is no treatment effect. I want to continue with this example. Let's start a new one. Our signal plus error over error ratio. We are making the same assumption. All error is the same. And let's assume our signal is twice the size of our error. So now we get an estimate of F that's 10, which is twice the size of our error, which is 5. So 10 plus 5 divided by 5 equals 15 divided by 5, and that equals 3. And what I'm going to tell you now, you can change the amount that our signal is. You can say our signal is 4 times the size of our error, right? Well, 4 times the size of our error, 5 times 4 is 20. 20 plus 5 divided by 5, 25 divided by 5 equals 5. So what you're going to see here is F minus 1 tells you the pure signal to noise ratio, right? And I think that's really interesting. Maybe you don't see it, but look here in the previous example, 10 over 5, our signal to noise ratio is 10 over 5. Well, that would be 2, but our F is 3. This is always the case. F minus 1 tells you your signal to noise ratio. And go back to your T statistic. T squared, your T value squared, is your F statistic. And if you look at the T distribution and imagine squaring it, getting rid of all the negatives and flipping it on itself like a pancake, maybe not a pancake, maybe a piece of pizza in New York, but still, you flip it on itself, and our T distribution becomes our F distribution. So for this problem, all we have to know is our signal to noise ratio for this within subject's design. So it's variance between divided by variance error. Variance between equals 127.75. Variance error equals 8.31. 127.5 divided by 8.31 is 15.337. Our signal to noise ratio is 15.37 minus 1, so our signal is 14.37 times the size of our noise. That's everything we know. This is the concept of the F ratio. And y'all, just for the future, we should just use the terms between, within, total, subjects, and error. I was simply describing what they were a little bit in detail so you would get an idea. Between is the between groups variation. Within is the within groups variation. Total is the total variation. Subjects is the participants variation. Error is crap that's left over. I don't mind if you use different words, really. Like if crap is better than error for you, I really don't care. But ultimately, these are the words I'm just going to use, and I'm going to be able to use them by just shortcutting, by using the shortcut. All right, so now it's time for your homework, and this page represents your homework. My goal is to make sure you understand everything that I was talking about today, so I'm going to test you on pretty much everything I was talking about today. The first thing that you need to understand are like the specific data sets that we use to calculate the various sums of squares. And I'll give you just a little quick review. Sum squares total is the entire data set when you ignore all the participants and you ignore all the conditions. So it's literally like one data set with all our observations in there. The sum squares between. Now, it is a data set that represents our means of each condition, but it also puts a mean of each condition in there for every observation in the data set. So if you look to the right, you're going to have to take that data set. You're going to have to put the mean of each condition in for every single observation in here. So you're going to have 3 numbers that are the same for the control, 3 that are the same for the 10 gram, and 3 that are the same for the 100 gram condition. Your sum squares within is just the variation within each of these 3 experimental conditions. And it's so you have 3 data sets there, and your sum squares within is calculated by summing those 3 data sets together, essentially. At least the sum squares of those 3 data sets together. And then your subjects data set, it's a lot like your between data set, except that every participant now, Mighty is going to have all the same numbers for the control, the 10 gram, and the 100 gram sleeping pill condition. Mickey's going to have the same 3 numbers for those 3 conditions, and Minnie's going to have those same 3 numbers for those same conditions, because what we're doing here is we're saying, hey, the average sleeping of these people is measurable, and it's a source of error variation that we can pinpoint and get rid of. In order to do that, we have to calculate the subject mean, and then we have to put that subject mean in place of that individual subject's scores for all 3 conditions. So we put Mighty's mean for all those 3 Mighty scores, we put Mickey's mean for all those 3 Mickey scores, and we put Minnie's mean for all those 3 Minnie scores. And so I'm basically giving you the answer here, and I'm okay with that, but I want you to see these are the data sets that we're getting our sum squares from. That's important for you to even do the problems without remembering all the formulas, right? This is how I can remember formulas without actually having them committed to memory, is I know what I'm doing. Now, define the degrees of freedom to grandma is my second homework task for you. Now, remember, I kept trying to explain this, and I don't know how well I am explaining this. But essentially, if we want to find the degrees of freedom for the total data set, that one's kind of easy. We say, oh, well, we got these 9 numbers here. How many of them are free to vary and still have the grand mean equal whatever our grand mean equals in this example, right? So it's like, hypothetically, these are the numbers we got, but what if these weren't the numbers we got and they were allowed to be anything in the world, right? How many of them are free to vary and still result in the same mean of this data, right? That's all degrees of freedom is. But you're going to have to translate that to your own words. So if you're translating what I'm saying right now, stop. Because I want to hear it in your words, maybe a better example than the one I have. So this is actually a challenge. Can one of you explain degrees of freedom better for me so I can explain it to other people better in the future? It's sort of like a favor to the future generations of students. For each of these altered data sets, I want you to show me the degrees of freedom like I did for you in this problem. So I want you to show me red and green. Green are free, red are not free. Then I would like you to use Excel for this, but take your data sets, calculate sum squares total, sum squares between, sum squares within, sum squares subjects, sum squares error. And then calculate your variance total, your variance between, your variance within, your variance subjects, your variance error. Variance is just degrees of freedom. Sums of squares over degrees of freedom. Calculate your F ratio, which is our best estimate of signal plus error divided by our best estimate of error, and interpret it correctly in terms of signal to noise ratio. And you'll notice this is a within groups design, so we actually have a really good estimate of error, and hint, it's not the within component.